So in a single loop, whatever resistance value, if you have two resistance, the maximum power will be transferred only when the two resistance values are same. So this R naught dash and this resistance value should be same. So that is what is given here. So even this you studied in Thevenin's theorem or maximum power transfer theorem, right? Then the final simplified equivalent circuit, you will have VTH, RTH, RL. For maximum power transfer, you blindly apply the condition RTH equal to RL, right? Same thing here also. I have only two resistance values. For maximum power transfer to take place from this AC source, which is available at the input side, the value of resistance R naught dash and this must be same. So R naught dash equal to omega square M square by Ri dash. So at this condition, I replace M by MC. MC is called the critical value of critical value of mutual inductance. This special condition, right? So I cannot use M everywhere. So I am replacing M by MC. So R naught dash equal to omega naught square MC square by Ra dash. Cross multiply R naught dash into Ra dash equal to omega naught square MC, or omega naught into MC is root of R naught into Ri. You know the expression for mutual inductance. I've told you in the class also. M is equal to K into root of L1 into L2. Correct. So this is a special case. So where M is going to be MC, so I'm replacing K by Kc. So MC equal to Kc into root of L1 L2. That is what I'm substituting here. So where Kc is the critical coefficient of coupling corresponding to MC. So find Kc. So Kc will be rearranged R naught Ri by omega naught into root of L1 L2. So even I can write this omega naught as root of omega naught into root of omega naught. So now I can group the terms. See here, R naught dash by omega naught L1 root power half into Ra dash by omega naught L2 power half. So this is one quality factor. I am writing it as 1 by root of Q naught 1. This is another quality factor. I am writing it as 1 by root of Q naught 2. So Kc is going to be the inverse of square root of Q naught 1 into Q naught 2. Okay, this is, we have derived a special case at critical value of mutual inductance. The coefficient of coupling also becomes critical. So at that point, we have found what is Kc. So we are also going to derive for a case which is not critical. So always you cannot say Kc or MC will be maximum, right? So they can be value ranging from 0 to 1. See, the coefficient of coupling can range from 0 to 1. So critical value of coupling means the value at which the coupling is maximum. So it need not be 1 always. In practical circuits, it may vary from 0 to 1, right? So what we have derived here is the ideal condition. At the critical value of coupling, we have found out what is the value of MC and what is the value of Kc. So now the next stage, we are going to do the same thing for the other case, general case, where the coefficient of coupling is not critical, the inductance is not critical. So I am going to do it for a generalized case. So again, this is a big derivation. So I think it is not advisable to continue because it will take another half an hour for doing this derivation. So I understand that what we have done is we have just stopped with finding out the critical coefficient of coupling and critical value of mutual inductance. See, single tune amplifier derivation was very simple. We just had a single LC circuit, so things were very simple for us. But for double tuned UC, since because we are having so many tuned circuit in the corrector side, we have to simplify all of them and make it simplified before even we can apply KVL or KCL. So that is why mathematically deriving double tune amplifier is very, very complex and you cannot remember the steps also. It will be confusing. One place instead of R naught dash, if you put R naught, then you don't know where you put R naught. So it is going to create a lot of confusion. So please understand double tune amplifiers as carefully as possible. And derivation also step by step, if you derive, it is going to be simple. But again, you should know in what step, what approximation or what terms you're going to neglect. So that way only you can remember the double tune amplifier derivation easily. Okay.